Uh, let's see, the camera, it seems to be not so very well clear. I don't know why, but I hope that you can see me. Thank you to be here for the lecture of today. Let me recap with two words what we did exactly at the end. At the end, I told you in the sense we analyzed um, this controller, which is in a no, this I think huh, you know that I don't remember exactly because it seems if I look at these calculations here, now really I am confused because this is another thing. Because these calculations here are related to place the eigenvalue, if you look uh, with respect to a system which consists in a p state controller. Is this one? Let me focus. Why it doesn't work the focus now? It's not so nice this focus today. Let me a little bit better now. Is related to this scheme. Not possible to see. Today, let me focus again. I don't have able to put a good focus today. Hmm. Better? No, it doesn't work. Why doesn't it work today? Okay, a little bit better, not much. No? Look at the scheme here. Let me take something to indicate better. Look at the scheme at the end. The scheme at the end was the last scheme, which I didn't simulate, but you can simulate easily at home. This is a good exercise for the examination. Starting from the file which I sent you, the M file and the Simulink file. This is a P controller combined with state space control. P controller combined with state space control. This was a P controller alone. If you look at the material which you can find in the email, you can see the theoretical, let me say, the analytical analysis. Here was a state space controller combined with the feed-forward control. In the preview emails, you can find also this one. What I didn't send you, but is extremely easy to do, is a PD controller. In the context, the analysis was in the context of the state space again. Of course, you can also consider a variation PD controller and the state space controller based uh, on what I told you during these 2 or 3 lectures. We conclude with this. P controller, which we are considering here to let me say, act on the error. And the combination with the state space controller. Why this concept here? Do you remember to cancel this at the end of the lecture? Why we analyze we don't need this? We don't need this. You remember this? I recall. Because if you look here, we have that the sensor characterized by the gain, let me say, your parameter K12, exactly what we had here with me. is basically, let me say, linearly depending with the other sensor characterized by Kp. I don't know. Um, of course, I can, I can, in the context um, of placing the eigenvalue, I can cancel. But we have to consider this. This is just a consideration that this Kp act also in the input map of the controlled system. Let me see if I find quickly. Act also in B. Now it's not the problem if I cancel this K12 because do you remember nevertheless we can play with R of t. I don't know if you remember, uh, but sometimes no we can consider to cancel, but practically now let me see if I can be a little bit more precise. Practically, if this is not so extremely expansive, we don't cancel, no? We don't throw away because we have a more freedom, no? Uh, to control to control the system. What I would intend is this one, no? Kp appear also here. This means to obtain the final value, then we have to work with R of t. I don't know. I don't know if you remember this concept. No? I don't know if you remember this concept. This means what I would like to say at the end to summarize what we discussed in depth last time. If really this is not so to have two sensors or to organize the control with the K11, K12, I don't remember the name, K11 and K12 is not so expensive in general. We don't cancel because, or we used because to have a more freedom in control uh, allows to be more flexible. No? Otherwise, do you remember we have to place with R of t. No? You remember with R of t. It is nevertheless possible because R of t is in a signal which we can choose. This means it's not a big problem. But here, in accordance with the placement of the eigenvalue, here is not necessary to have no? Kp, excuse, K12. Kp must be there. I mean, how possible to say? I cannot put zero. Of course, I can fix the value, one. But in this case, uh, we don't speak about the P controller. No? This is a little bit in a contradiction. If I introduce the P controller and then I fix, but nevertheless it's possible. Nevertheless, it's possible because Kp uh, uh, nevertheless. This means typically we don't cancel, we don't eliminate. This is the idea. But in the lecture, in the analysis, you have to consider that at least here, if some time is necessary, this K12 could be considered equal zero. No? But of course, if we consider equal zero, we have to consider that Kp is connected with the input. This means the choice of R of t, I don't know if you remember the lecture last time, is constrained, but it's possible because R of t can be chosen as we want. We have many elements, let me say, to be designed. If you read again, let me say, the lecture in YouTube, you can, or you look at the material, is everything is written. You can see what I intend. Okay, let me do now the most important part, the final part of this state combination on this selected control strategies. Let me reorganize the material a little bit better. Otherwise, I lose everything again. Give me 1 minute. Uh, Let me see. Let me reorganize here. Oh, okay, this here. Just in second is a little bit boring for you, but if I lose the material, then I cannot, because the idea is to send you also per emails in this case, um, the whole material concerning one topic, no? Classical selected topic, uh, and then you can find in one email everything there. Oh, where is now this? When I try to move the material to show you better, I lose always. Okay, here now. Okay, I lose the page. Unbelievable. Unbelievable. Okay, I will organize. So, okay, let me now go ahead with the lecture of today, which is the most important part. But please try to do at home, reading the lecture, of course. This exercise, no? Which one? To implement P controller together or combined with the state space controller. PD controller combine also once alone, uh, also P alone, and PD controller alone, and then PD combined with state space. We will see that extremely easy to realize some specification. You can invent a specification inspired by what I specified. You remember, I don't remember, without oscillations, rising time, I don't remember, 1 second as you want. Uh, you realize very easily that if you have more parameters to be set, it's easy to achieve the goals. I don't need to explain this. Of course, more parameters means, nevertheless, something which is more expensive because more parameters means probably more sensors or and also a little bit more calculations in the microcontroller. Now the calculations is not really a big problem because we have seen that at this moment the controllers which we have seen is just the multiplication of the signal which should be inside the controller multiply in a constant. But nevertheless, if I have more signal to be processed because we have K12 and KP, of course we need some I don't know if you know probably, but you know analogs, discrete conditionings part in the hardware. Anyway, more information you have to process, uh, more expensive is the system, no? Because also this AD system, analog discrete, nevertheless costs something. And not only the cost, if it's there, must be maintained. Sometimes they will broken down. Anyway, if we achieve the goal with a less number of sensors uh, or less number of equipment, less number of calculation, yeah, of course, calculations is always better. Now, very important is because very often the question in the project is related to this control scheme because it's the most used, is the most important for different reasons. I will upload in any case in our platform. I will send you also per email and so on. Again, the system which we considered until now. Don't change the system in order to be able, if you want to do at home, to compare the result and so on. Now, let me consider I1, which is our, I see, excuse me, which is our input, which is output of the controller, in this form here. Basically, I do the integral as before, excuse me, the error as before. Do you remember? Error reference. Let me say what I want to obtain. Please pay attention. R is what I want to obtain typically, but if I need a particular R, reference signal, to obtain something different, this is possible. You remember, I told you this concept here. Not only if I don't have the possibility to, I mean, in case I need an element to fix the goal because I have too few parameters. Do you remember I told you before K12 I can eliminate, I can put equal 0. But in this case, to achieve U2 5 volts, if you look at the past lecture, you can understand better what I intend. I need to put a particular R of t because R of t is 5 volts if I have enough. Remember, I told you this. If I have enough parameter to place the eigenvalues and to fix the goal. Of course, I can renounce to fix all eigenvalues. About that, I told you a lot. But anyway, we go ahead now easily. Error between what I want to obtain, assuming that this is what I want to obtain. Could be also different. But if it's different, it's something which help to obtain what I want to obtain. Nevertheless, this can be given. In the easy form is exactly what I want to obtain, the reference. Minus what I have. This is the error. If I don't consider, we call this error. If I don't consider, the integral is exactly my P component of the control. Now, very interesting. I consider the integral. This is a totally different control strategies, totally different control. In order to understand, today the focus is really, it's better, I don't know. I try to improve, but I think I didn't improve much. Okay, I hope that you can see it. Look at this. In order to go in depth on this controller, I will consider xi of t exactly the integral. This is not much different if you think. No? But conceptually, what I am doing with this position is that I fix just the integral. I isolate it, just the integral, if you think, in a new variable, which I will call pseudo state variable, or if you want, state variable of the controller. Why that? In order to understand better, look a little bit this equation. Yeah, but I can consider also a different equation. I can consider also here I'm considering a capacitor, no? But I can consider also an inductance in the same way. But let me consider this. But I already introduced the concept of the state exactly thinking on integral. Do you remember at the beginning of our course in maths? Emerge. I told you that anytime, anywhere, when I have an integral, I have a state. Because in our conception, in our approach, the state variable, or the state variables, in plural, means the capability to store energy, or in general, to store. Here, in general, I will store voltage or load in the capacitance. in an inductance. In the same way, if you remember, I told you about an inductance. We store magnetic energy. Here, better to say we stored through UC, which is the state, uh, lowered or electrostatic energy in a capacitor, in an inductance, we stored electromagnetic energy, and we represented the electromagnetic energy with the current. No? Here we represented the lowered or the electrostatic energy, better to say the electrostatic energy you use in UC, the voltage. I forgot that I have it. Of course, here we are speaking about two, let me say, physical energies, which we can do a more direct experience. No? The load is in the capacitance, the electrostatic energy in the capacitance, the magnetic energy in the coil. Here, it's a little bit more difficult to speak about a direct, let me say, experience or direct, we cannot perceive directly this energy inside. But if you think about them mathematically, the integral, we have nevertheless three integrals. What is the advantage of this idea here? In any case, in accordance with our approach, in any case which we have an integral, we have to consider the possibility to define an energy or a pseudo energy, and this means in a state. Remember the correspondence between state and energy, or the pseudo state. What is the advantage? The advantage is I can consider now the dynamics of the controller at the end, because the dynamics means basically, or is the capability of a system to store, to change. And the changes in my controller basically is this one, because the derivative of xi, this pseudo state with respect to the time, is exactly this. Is exactly this. And the output of the controller, which is the input of the system, is this: k1 multiply xi. Do you remember when I told you about the matrix A, B, C, D? I think I told you, no? In the linear representation, of course I told you. But it's intuitive. Which we have here. The possibility to include, I will do it now, also the state in the state representation of the controlled system. Here is clear what I'm doing. Before going ahead, I would like to summarize everything, saying that this controller is totally different with respect to the controllers which we have seen until now. P controller, PD controller, state space controller, state space combined with feed-forward controller, state space combined with P controller, state space combined with D controller, state space combined with PD controller. The reason is that this controller consists of a memory. Memory equals state. Memory equals integral, because we can accumulate, let me say, pseudo energy. Now, what I told you has as a consequence what I would like to tell you now. This is really a selected aspect, if you will. Look, instead of u1, I will put ki multiply xi. Because as I told you, u1, remember my last sentence, u1 is the output of the controller. That is the input of the system, ki multiply xi, in accordance with what I defined here. Again, a controller starts considering a definition, this one. let's consider now, no? The control and the sphere. The second equation does not change because we don't have a U1 always, no? So, yeah, at least for the system, of course, for the system. And then we have in the controlled system, in the representation of the controlled system, another equation. Which one? The dynamics of the controller. Now, the controller has no dynamics. Until now, we always worked with two equations. Do you remember? Because the controller until now didn't change the order of the controlled system. Here, yes. Here we have another equation because we have an higher order of the controlled system because the controller which we included consists of a memory, consists of an integral, consists of a dynamics. Now, do you remember I told you the matrix is A, B, C, and so on? Now, without going the formalisms, we can see as the new A in some books AC. I told you also last time we did AC here. No? Hmm? Here we have the derivative of the augmented state in which we have an xi. The augmented state is here. No? As before, I1, U2, that does not change. The physical, let me say, the physical state, which represent the physical energy. Here we have another state, we represent another pseudo state, if you want. Even though I don't want to use pseudo, but augmented state. Why that? Because if you look here, we have nevertheless an integral of the voltage, no? An error of the voltage. This means if you want, uh, we have to do somehow with in any case with something which is related to the physical energy. Of course, pseudo in some books we can justify because yeah, it's not exactly, it's something which I will introduce to control. The sense is not properly of the system. But anyway, you can call it whatever you want. Whatever you want. Okay. Look now at the matrix. It's very important. But we already did this exercise a little bit easier when we considered the other kind of control. But let me go in depth here because believe me, this kind of controller is very used for the reason which we can understand. Of course, we can image some advantages. But the drawback we have seen already now that we have an order more. This means more computations, more problems to place the eigenvalue. Now we have to place three eigenvalues instead of two. We can image directly now that we have some drawbacks. Of course, we have some drawbacks. Three eigenvalues instead of two. Calculation load higher because we have a matrix is, let me say, is quickly larger. But let me go in depth. Three states, three states derivative. I don't have to clarify the structure of this because it's exactly the same as before. Let me investigate the matrix AC. Let me call here the matrix AC and the matrix BC, no? Controlled. B controlled, A controlled AC. This line in the middle, we don't need to comment because this element is as before, this element is as before, this element is zero because xi is not represented in the equation in the middle. Easy also this one because this one represented this equation here, and then we have here uh, to represent this, which is rho multiplied column minus u2 as a function of uh, U2, and 1 because we have R of t. Here, I forgot to comment, we don't have R of t, this means 0, no? This position. It's the same trick which we explained in detail last time. Here is the difference is that we have three states. We have three states instead of two. I mean, I think to justify this, this is enough if you want to look what, as last time, what we have here, what we have here. Of course, yeah, if the goal is I1, instead of U2 is I1, of course, the change that R is not a voltage, or it's not related to a voltage, but it's not a voltage, it's a current. If I have a I1, we have here 0, if you have -1 here. In case in the exam I will ask, please control the current. I can control whatever I want. I told you about that. Uh, I can control also the resistance, the voltage on the resistance. And in this case, it's exactly the voltage in the mm, capacitor. I can control also the voltage um, in the coil. Try to do this at home. It's not difficult. Try to do this at home. Again, exercise. Try to control the voltage on the capacitance. Excuse me, the voltage of the capacitor is this one. The voltage on the coil, as an exercise. Uh, it's not so extremely difficult, believe me. Mm, okay, I have to look at this. Why these two elements does not change? Again, this remember is always always also depends. It depends. Because you remember change if I have a state space controller. Let me go directly here without comparing. This easier. This is 0. This is -1 divided L because we can see that here we don't have any component which depends of IL, therefore 0. -1 divided L is this one, which is multiplied by U2. Let me consider easy approach. Just look here and look here how I can represent. Why chi I divided L? Because chi I divided L, in accordance with what I have here, multiply xi, let me say the state related to the integral. Easy. 0 because we don't have here R. Let me see if I forgot to say something, but I don't think so. Uh, I I think I don't think so. Try to do at home, or to think about also today to control UL, the voltage on the coil. Could be a good exercise. Later I will give you an indication if you want, but it's extremely easy. Look now at some considerations, and then we will go ahead combining this integral controller with the state space controller. Why we need it's in a possible variation, very often used because with this ki, I can place just one eigenvalue. We have one parameter and three eigenvalues to be placed because, of course, the dynamics consists now of three dynamics, which are connected to each other. You can see that with the presence of Ki, the dynamics of the controller comes directly in the dynamics of the current. The dynamics of the current influences the dynamic of the U2 because of this element here. And the dynamics of U2 influences the dynamics of the controller. Is here, you too. No? This means the system is totally interconnected. Must be so. Must be. I mean, we can control because the system is interconnected. Before considering a combination of this controller with the state space, for instance, of course, you can consider atom as a possible exercise. It's not much different, the combination with the P controller, with the combination with the D controller. PID and PID allows to place the eigenvalues. Do you remember this? We have three parameters and three eigenvalues to be placed. Okay, let me go ahead with this consideration. As I told you, I can place just an eigenvalue, but choosing Ki, which guarantees the asymptotical stability of the controlled system, we have, assuming that this is not the problem, what is this sentence here? Assuming that this is not the problem, because it could be that the system remain stable. We have to be careful. Do you remember I told you a lot last time? We have to be careful if I can place just a part of eigenvalue, because it could be that the dynamics is not let me say good in general. In this case, in this particular case, because we have this augmentation, and in particular because we exceed the order 2, of course, the system can become also unstable. Please pay attention and this concept here. I think I told you last time about many aspects about this. Here with three eigenvalues, we have to really be careful for the stability of the system. Also with two eigenvalues, we have to be careful if I don't have two parameters, because it depends of the sign of the parameter. It could also be unstable. No? With positive parameter, no. Of course, it depends, no? But it depends nevertheless on the system. The system which we have seen, we cannot. But in any case, or at least the example which I put. But in any case, please, as a general indication, please pay attention. But in general, for K, but I told you, remember, Kp positive, Kp negative, also last time. This means in general, we cannot say that the system remains stable. No? We have to be careful. Do you remember in case of Kp, I analyzed, if you look at the video, if you look at the material, I analyzed also the possibility to become unstable also with two states. In any case, a little bit more difficult. Here is extremely easy to end up with an instability. In general, we cannot guarantee the stability if you don't have enough, let me say, roughly speaking, coefficient. Last time, I do remember, I tried to distinguish Kp larger than -1, -1, something like that, no? Particular negative, positive, something like that. Look at the lecture. But what I want to emphasize here, um, assuming that we have the stability, because it's not necessarily unstable, no? If R of t is a constant, as always, no? This is I didn't put as an hypothesis, because it's always in this analysis I didn't consider R of t as the signal. Does not change much, but yeah, at this moment we are considering an R of t which is constant, or at least constant with t relatively large. But let me say constant. Remember, I told you this. But because of the assumption of asymptotic stability, assuming that is asymptotic stable, that means it is possible, no? You have to choose carefully the parameter ki, in particular in this case here, which we started from an asymptotically stable system, no? Our R, very important RLC circuit. Uh, this means um, let me show uh, this sentence a little bit better, exactly from um, intuitively from this consideration here. I told you that is R of t is constant, and the system is asymptotically stable. We have thus the u of t, u2 of t, and I1 of t will converge to a constant because we have a system which basically is asymptotically stable, means dissipative. No? We will find, I don't know if you remember a little bit what I told you, or for difference course, we will achieve constant I1 and constant U2 because we have a constant in input. The system means is dissipative. We dissipate energy. We cannot diverge. This means I go in input with a constant, I will go out with a constant. This will be zero, this will be zero. This means this is a constant. If this is a constant, I want a constant. And you can see from here that these two, as I told you, is a constant. And how possible to explain better? Yeah, and I can show you, for instance, in this circuit, very let me say, yeah, very easy if you remember the structure, which we have. Let me see how I can. Yeah. The input U1, which is the voltage, no? This is the output of the controller, is exactly the voltage of the capacitance because of the constant of I1, the current I1, the coil becomes a short circuit. I don't know if you remember a little bit, yeah, this electrotechnic concept. This electrotechnic concept, I1 is a constant because, as I told you, if U2 is a constant, I1 is a constant, but is zero because is the current which is passing through the inductance. No? This means U1 is equal U2. Sense. This means that the reference is exactly U2, is exactly what I am trying to express here. More mathematically, if you think about this equation here, probably it's more easy to analyze mathematically. As I told you, this is zero because everything, if I have a constant in input, R of t is in constant, we have also constant in the state. Have a constant also in the state because of the dissipativity. We cannot diverge the set because we have eigenvalues with the real part negative. if you look here, this is 0. This I told you is in a constant. This means xi is in a constant. It could be easy to analyze in the mathematical form. Xi is in a constant because this is in a constant, this is 0. If xi is in a constant, the derivative of xi with respect to t is 0. This is a little bit, the idea. This means, this is probably is more easy to be analyzed as u2 for t infinite, which we judge the asymptotical stability. You remember, the asymptotical stability means to judge for t infinite. The word asymptotically, this means to t infinite. R of t equal u2, or u2 equals R of t. Okay, let me go ahead now with the combination, I think. Okay, here there is the explanation a little bit exactly what I told you about the long explanation about about what I told you until now. I will scan, I will send you. It's just exactly uh, with the different words what I tried to explain with R constant and so on. We don't need to repeat again. Very important now. Here, this part I would like to skip, but think about that I can consider also R of t as a possible state variable, but I don't want to go in depth on this in any case. But you remember, it's not new to consider R of t something which I can determine. What is nice now? Let me show you. Let me see if I have here. This I would like to skip again because it's related to R of t. This I would like to skip. What is important now is exactly the combination, because this is really a selected aspect which I would like to discuss with you. And then we take a rest a little bit. No? Look, we have as a new definition, please pay attention, definition of the controller, the combination with the P controller. Then we will see the most important with the combination of this controller with the state space control. Let me do this calculation not very quickly, and I will leave the exercise for you. But I will do an exercise including MATLAB Simulink for the most important of, let's say, combination, integral and state space. But let me start with the integral with PI controller. Even though it's not so important as a P state controller, but nevertheless it's used. No? It's used, PI controller, proportional integral controller. Try to redo this at home to simulate. Now we'll discuss advantages and drawbacks, and try to do at home PID controller. No? Try to do at home. But let me go ahead together with this. Easy. Instead of U1, I will put this one. 1 divided U1. This time consists of this form here in which xi is the new state or pseudo state. This equation is the same. I will add this equation doing the same consideration as before. Here we have U1, no? The output of the controller is the input of the system. Matrix representation. Now it is not is new now. is exactly, let me say, as before, but here we have in KP. You remember before we had minus 1 divided L because KP was 0. Uh, don't want to say 0. Was not considered. But of course, yeah, we can consider 0 in this representation. In this representation. But I don't need now to repeat this, no? Because KP divided L, of course, will multiply U2. We can see from here with minus, no? Kp minus U2 divided L. It is here, no? This minus is here. Multiply U2. Minus 1 divided L multiply U2 is from the system, no? Structure. Is the structure of this. I can place here just two eigenvalues. And then we have also the constraint here. Yes, it's not a problem because I can work also with R. No? R could be determined in order to obtain U2. Think about also at home but the limit here, if it's a limit, is not a big limit because we can nevertheless obtain an asymptotical stable system. We have to be careful, no? Because one eigenvalue, you remember last time I told you a lot, is automatically placed, or the position depends on Ki, on Kp. We cannot directly or arbitrarily place, but just indirectly. But indirectly means if you work carefully means, remember, do the calculation looking at the root of the polynomial characteristics. Here we have three eigenvalues, no? We can see as the three eigenvalues will move as a function of Ki and Kp, but I cannot place arbitrarily three, just two. And one will be where will be in accordance with the structure of the characteristic polynomial. We have seen this exercise for an easy example with two states, but here it's just a little bit more boring. Therefore, I don't do. Okay. Let me see if I forgot to say something. The consideration, no. This is just the same as before, no? Because we have a part of the controller within memory. Let me see if I forgot to say something. I don't think so. Okay. Try to do at home the simulation if you want to think about how we'll move the eigenvalues for given Kp and Ki. I mean, try to find a solution of the polynomial characteristic as a function of Ki, Kp. Please pay attention that we have a polynomial order 3. This means we can find just numerically in general, numerically the position of the eigenvalues. Because it's not the polynomial of the second order, therefore I don't do because you will lose interest to stay to the lecture. Now look, this is more important and we will do the simulations. But the simulation for this is not different. A little bit different, the analysis of the position of the eigenvalues because theoretically must be done numerically. Here we don't need, we can work with place because we have three parameters and three equations. Now we can see the combination integral and the state space. Representation, the same consideration as at the beginning. No questions about how I can represent xi, no? Or the state of the controller, or the part of the controller which consists of an integral. Um, Mm. Yeah. Instead of u1, we have this expression, which I put explicitly. Here we have the product between the, remember, the row matrix K and the column states. We have this here, these two elements. This element here is that. This does not change as before, this does not change. This means now no problems to represent these expressions here. It just what change is this line here. We have a K12, this is really now a habit because now we don't have a Kp which multiply U2, we have a or beta which multiply minus U2, we have a K12 which multiply U2. And here we have a K11 which multiply I1 because of this element here. Everything came from the state space control. And this state space means in a structure we consider the linear combination of the states, row multiply column. Very important, this part here, the part of the memory is always the same, always characterized by a new state, an augmented state, pseudo state, as you want. Does not change basically conceptually nothing, but of course you have to be careful to reproduce uh, this information inside the matrix structure. Again, R of t is constant. Here I put some comment about that. As I told you, do you remember the xi, the derivative of xi with respect to the time is zero in case R of t is constant. But until now, we considered always constant. Constant. What I would like to say now at the end, before simulating, before analyzing more in depth with the simulation, but I think we take a rest a little bit. One important aspect, which one? The robustness of this scheme at the end. At the end, and in particular, analyzing the basic structure at the beginning, but in any case, when we have the presence of the integral, please keep in mind, if, where is now? Now to find the material here. Let me repeat. In the presence, oh, why I lose everything? Every time when we have an integral, and please pay attention, Rn is constant. Look at this sentence here. We have a steady state error which does not depend on the parameters. Here I put this at the end in order to summarize every times which we have the presence of integral in the controller. It doesn't matter if combined with P controller. It doesn't matter if combined with D controller. It doesn't matter if combined with everything which I have, PID, E with states. We have a robustness steady state, but in case R is constant. If it's not is constant, we don't have this, of course. But robustness in terms of steady state means exactly this. That I will achieve the goal, which I fixed, or indirectly, which I fixed. But let me say I fix R of t equal the goal. But you remember, I told you can use also R of t to achieve the goal, which is not exactly R of t. But let me consider the easy example. R of t is our goal. I will achieve the goal. Here, very important to notice, independently of the knowledge of R, L, and C. We can see from here. What I told you before holds always when in the controller we have the integral. If this holds exactly what I told you now. Of course, steady state. Steady state. Excuse me. Steady state means for t large enough, theoretically infinite. Because this consideration here is valid as you look at this slide for its possible combination. Assuming that, very important, that we have the asymptotic stability. Therefore, I told you we have to be careful placing the eigenvalues. This means we have a dissipative system. If I go inside with the constant, I will go out in the state with constant. But if the state is constant, it doesn't matter which kind of controller I will obtain. We have U2 constant, I1 constant. This means at the end it doesn't matter. Also from here, we have xi constant. But if I is constant, this is 0. This means steady state, U2 equal R of t. In this combination, in P combination, uh, if you look, you will see exactly what I intend. Let me see if I forgot something. The reason is that steady state, the integral introduced this robustness, this robustness concept. Let me think if I forgot to say something, because the correction is done through the integral. I will add, let me say, through the time, the integral of the error, and I will correct this. Think about that, but mathematically, I showed you. Let me see if I can add something. Also here, if asymptotically stable, this is 0, is asymptotically stable, this is 0. If this is constant, this is an hypothesis, this is constant, we have the xi is constant. This is constant, huh? Everything is constant, this means this is constant. Think about xi equals 0 and plus this element minus this element, which is constant. This means the derivative is 0. This means steady state, u2 steady state, t large enough or infinite, equals R of t. In any scheme, try to do at home, which we have an integral. To explain physically the best explanation that I am correcting the integral. No? This means yeah, how possible to say that xi is constant and will compensate the difference. And the I with the t is 0. Steady state, of course, steady state. This means U2 infinite equal RT infinite. This is a little bit abstract, this concept here, physically. But mathematically, you can see here. Of course, the asymptotic stability must be given. R of t must be constant. Otherwise, not. We will see. Okay, I think we need a little bit to, we have just 1.5 hours, more or less. I think we take a rest a little bit. I try to organize this material. And then when I come back, let me see what I have to tell you. I think we can start directly with the simulation of this. This is extremely important, which is in a basic file, which I want to send you, which I want to upload in the electronic platform, which you can consider a possible example to be modified if I ask in the project, try to consider an PID, try to consider, I don't know what, but based on this. No? This means the modification, you have to think a little bit, consider also the lecture. It is not so difficult to build the model in terms of different specifications. Or probably sometimes I give directly this example with different questions. nevertheless topics which we considered here. No? This is basically the idea of the projects, to redo eventually something different, but not much different, what we described here, based on the software which you can find in my emails or in your electronic campus, let me say. Okay, give me 20 minutes, more or less, 10 past 3. uh, so I organize here, I look for the next topic, and because with this, I mean, the simulation, and then simulation, of course, because this, in my opinion, sum up these selecting aspects. Selecting aspect means this PID, this classical controller, also integral, so, but inside this state space structure. We will see here in 10 minutes, 20 minutes, excuse me. Okay, let me now simulate this scenario, the last one. The last one was a combination between the integral action, extremely important in our application because allows to say that it will converge steady state if r of t is a constant independently on the knowledge of RLC in our specific case. Without bias, basically. Do you remember about the bias I told you? And also I simulated when I think in different scenario, in which I told you that if we don't know the parameters, uh, we generate an error in a steady state, which is an error which is something which we try to avoid. The reason is that an steady state error means that the goal is not achieved, or not achieved completely. Excuse me. The integral, if R is constant, allows this independently of the knowledge of the parameters. Of course, what changes the transit, what changes the transit, but the integral compensate this lack of knowledge because it's acting on the integral. Think about physicalis is a little bit difficult to understand, but mathematically we have seen together. I think I didn't forget anything. Let me analyze now the M file. Let me run the M file, change folder. Again, I give you the values. Ah, we can see the matrix A is the matrix of the system, as we have seen also last time, and we have seen today also in the lecture. It's the matrix A, the dynamics, the linear system, of course, at this moment. We will see, starting from today, this assumption of the linearity will be removed. We will see that using the sliding mode control, we can consider also non-linear system. Sliding mode control will work also for linear system. Let me go ahead here. B, the matrix B is known for the system. CM is a matrix which allows to say, I would like to look at the output of my simulation, in particular, everything. State I1 is state U2. D, if you remember, is a matrix which has the row of C and the column of B. This means it's a matrix with one columns and two rows. Because D consists of a number of column equals the number of column of B, and the number of rows equal the number of rows of C. I calculate the eigenvalue of my system. Then let me see. Yeah, this exercise we did also last time. Um, Basically, we don't need now. This means uh, let me skip this part here because you remember this part here we used last time for the n this feed forward action. Probably in the Simulink file we have both, you know, in order to compare. But we analyzed this part here also last time. I don't know if you remember. Basically, this was until here the combination of the feed forward action n and the feed forward action together with the state space controller. Therefore, we have in a system, the resulting system at the end with two states. Look at this case here. It's the case with integral. Now, A augmented is exactly the augmented matrix in which I include the dynamics of the integral. Here, nevertheless, it seems but I have to clarify something. Which one? Because about this augmented matrix, I didn't tell you in order to use, is there together with B augmented, in order to use the function place. Let me see if I find the material to clarify this. Otherwise, it's not so easy to be understood. Let me see. Let me look. Should be somewhere this promise to find. Otherwise, I will. I have it. I have it. I have it. I have it. Excuse me for this interruption, but I forgot that in the MATLAB file, I use this approach, which is a nice approach, but I forgot that I had. Let me come back quickly on the example which I did to understand basically this last part, and then we simulate directly. Again, the system is controlled by a combination between integral action through K1 in this sense and the state. Before I used Ki, also in the I don't remember in the MATLAB, but anyway, it's a parameter to be calculated. Xi we know. Excuse me, is Ki. It seems to be one, but it's Ki. We have IC from here. How typical, you know? It's anyway. We know everything. This I already explained, and I already explained also the matrix. Now, where come from this A augmented? This basically is the representation of the controlled system, which I don't need to be explained again. I already told you. Now, in order, there's just in a technical aspect in MATLAB. Sometimes I implement it with different support. But in this case, it's worthwhile to spend energy a little bit to look together where this comes from. One second. Yeah, yeah. Again, R of t constant. This I don't need to repeat. The idea is now to calculate K11, K12, Ki in order to place the eigenvalue arbitrarily. Arbitrarily means wherever I want. why I need to express this A extended, exactly what I told you until now. The matrix related to the controlled system. Hmm? This is the extent. Augment in the sense with the control, but we don't use augmented because augmented, we reserved the word augmented for another meaning. Here in this lecture, this is an extended because we extend the model to the controller. Huh? Here, I use this equation to say the dynamics, which includes the controller, this means system plus, let me say plus the controller, included the controller, I would like to write in this form. In a particular A augmented we will see together, minus in a particular B augmented, and K augmented defined in this form here. Exactly what we did until now. No? But now we will see more structure what happens. K11, K12, Ki. We have seen something similar, but without Ki, no? Without Ki. Now, what is B augmented? B augmented, we don't have doubts about B augmented because the input comes, let me say, from the first dynamics, this 1L. 0 is nevertheless 0. This is basically these two elements of the system. And the last element is 0 because has nothing to do with the controller. This is easy to be performed. Basically reflects the B, and at the end we have the B of the system 0 because the controller, which is reflected here, cannot go inside in the last line. It's go inside here. B multiply K augmented, B augmented, K augmented is related to a system with not the states, the third one. This means respect the structure of the system. And the 0 because we don't have anything to do with the with the third line. The third line is the augmented line in the sense the last row in the set of the system. Now, what is A augmented? If we fixed K augmented because we want to have in accordance to the function placed in this form here, B augmented reflects our input map. A augmented is calculated considering A extended plus B augmented, K augmented. Again, A augmented in order to use place. This is the form which we use in place. If you digit help place, we have this form. But what is A augmented? Is the matrix which we have plus B augmented, K augmented. Look. If this is A extended, exactly what we have seen many times. We have seen before. We have seen exactly now. This is A augmented. Why that? Because if I add this plus this matrix is then a 3 times 3, because it's the product between a column with 3 row and a row with 3 column. Excuse me. And a column with 3 row is the row with 3 column. Okay. I don't know if it's visible. Is this? Okay, it's just the results. The product between this column and this row is the matrix 3 times 3, in which we have in the first line of the row 1 divided L multiply K11, and then 1 divided L multiply K12, and then at the end of the row 1 divided L Ki. And then the rest is everywhere 0. But if I sum this plus this 3 times 3 matrix, I will obtain this. It's easy to see. how I can quickly find this? It's extremely easy. Put to zero the parameter k11, k12, and ki. We can see k11, k12, ki from the uh, A extended, no, the original matrix. You have A augmented. This, I can use this in the structural place in MATLAB. It's in a technical aspect, no? See, it's in a technical aspect because the function place, given an augmented matrix and B augmented, I call augmented, but in any kind of matrix, state matrix A, any kind of input matrix B, and the desired vector of lambda, I will obtain the matrix K such that, matrix in row K, such that B multiply K, I will reobtain the matrix A extended, let me so, but with fixed value K11, K12, Ki, which realize my dynamics. I think if I show you what I intend in MATLAB, it's easy than to use many words. It's in a technical aspect to be able to use the function place. From the lecture, I have A extended. I put to zero all parameters here. If you want, I can comment a little bit. Could help. Let me write so. Again, P augmented reflect the P of the system, the B of B augmented reflects the B of the system, but at the position, let me say 3, 1, this here, I put zero because nothing to do with the matrix K. Now I fix arbitrarily, please pay attention, three eigenvalues. Now, arbitrarily means in our case, look here, look here. Lambda was the lambda 1, lambda 2 was the eigenvalue of the original system. We can see that I am considering at least 10 times faster in the new dynamics, at least, and without oscillation, because I am considering the real part of the eigenvalue. Lambda are the eigenvalue of the original system. Original means the physical system. This means at the end, I would like to obtain, at least in the system, 10 times faster. Let me so roughly speaking, not 10 times faster, because of course, to be really estimated here, we have three exponential functions, which the answer is given, you remember, by the sum of these three exponential functions. This means to say that 10 times faster, I don't know if it's precise, but let me say so. I don't know if it's precise. Because precise is to say at least 10 times plus 20 times plus 3 times faster. If faster, if the measure of the speed is really just related to lambda, that can be acceptable. Because it's the sum of three exponential functions. If I assume that the velocity, the speed of the answer is related to the eigenvalues, I can say so. And then I apply the directly place. Then I have an augmented function. Let me show you. An augmented matrix and a row matrix. We can see here. Okay, let me open Simulink. Okay. It's not possible to open this file. This means I have to consider another version of MATLAB because probably I opened with a new version. Let me see if I find quickly. Let me close this MATLAB. Excuse me for the trouble. It could be that I opened the file with the new version of MATLAB, and this is, let me see. Otherwise, I look for the material because to rebuild it takes time, but I can do that. It's not so a big problem. Let me see if I able to open the file using the new version of MATLAB. Okay, it's lovely. Let me share again. I hope that I can be, otherwise I can rebuild. No, not a problem, but we we save a little bit time. I think you can see now MATLAB, it's lovely. I hope you can see now. Yeah. Let me come back ah, to our. Okay. Okay, let me open again this. This is the file which I already commented today now. Let me see. Okay, this is the comment which I put now. Let me run. Now let me try to open this Simulink file, and I hope that now I can read it. If no, okay, in this case, I will try to rebuild. Okay, I can read it. Very nice. Mm. Okay, let me comment a little bit. Let me restart a little bit, comment it again the model, because could help in any case. Because when I give you the project, basically I give you the equations, and then the first question is to build the block diagram, and then to reflect the block diagram in the Simulink model. Current, I1, derivative of the current, I1. in between we have the integral. We have seen. Huh? Why this element here? This element here is again in which if you go inside, you can see that we have one divided L. Let me show you because we have a particularity. In order to test the robustness, I didn't put L. You can see here. But I put, I mean, to design K11, K12, Ki, I put L. If you remember the M file. But here, to test the robustness, I put a 10% error. But basically it's an L, but it's an L which I don't know exactly. I mean, I designed everything using L. But the real value is 10% larger than the value which I used in the design. Excuse me again for this trouble. Here we have basically the signal in the equation, let me say, is basically UL. I indicated here because it's basically U1 minus U2. I don't know if you remember the equation or if you remember the scheme. No? Therefore, I put UL, the voltage on the inductance. We can see a U1 minus U2. How I build this element? Yes, it's basically the same. No? U2 between U2 and the derivative is integral. Inside the integral, I have to put the initial condition. If I don't put MATLAB, put 0. Here, we have, I don't know, if you remember here, we have the current balance. U1 minus UR is the current which is passing through the capacitance. No? In fact, here we have 1 divided the capacitance. But of course, also here, I try to perturbate. Technically, this lack of knowledge, I think we say epistemic uncertainties. This means we don't have exactly knowledge about. Parametric uncertainty, probably easy to say. U2 divided R is exactly the current passing through the resistance, passing through, let me say so. Now, control system. We designed a control system consider the ideal parameters. The goal is 1. Now I can fix directly the goal here because we have enough. We don't have a mismatch. I told you a lot about that. 1 is the voltage which I would like to have here, which is exactly in the reference. Remember, I told you a lot about the R. Here is exactly my controller, which states, at least here, the two eigenvalues using 2 parameters. Parameters 1 of the matrix K, parameter 2, let me say 2. I mean, K augmented 1 is K11. K augmented 2 is K12. I think we used this notation. K11, K12, and Ki in the lecture. I don't remember now. Yeah, I think it's this. But anyway, the first element of the K augmented, the second element of K augmented, I think this is the notation. Yeah, it's this one, I hope. I have always the problem to find the material with this confusion. But anyway, it's clear what I did. You have a plus here because mine I included here. No? Do you remember this concept of the minus? I told you many times. It's also here, and a minus. Basically, the matrix K augmentis is always in minus. This element with minus here, the third one is represent Ki, and all elements here is minus. But if you remember, this K augmentis, even though with a minus, is multiplied by the reference minus U2. But also this is responsible to place in our selected specific frame, is responsible for placing the eigenvalues. And then we have the integral. Think about 1 second, then we will simulate. Idea is to show you that steady state we will converge to one even in the presence of parametric uncertainties. Let me show you. Let me run. To be precise, should be nice if I compare here. Let me show you with one. I hope that I share. I don't know. I share, yeah. Let me run again. Let me simulate shorter. 100 seconds is too long. I don't know, extremely long. Let me see 1 second because do you remember we have I didn't check the lambda, but 10 times, 20 times, I suppose that. Also, this is too long. What I am doing? Look, I would like to clarify because this is also technical is important. Technical is important. Look, lambda. Look, the system consists of these two eigenvalues. The real part is responsible for the, let me say directly, the real part is the imaginary part can be seen as the sinus cosinus. I don't know if you remember in the math of the solution of the differential equation. The real part is basically the weighting, or better to say, the exponential part. This means 166 more or less, no? Because it's multiplied by 10 up to 3. No? This notation here means 10 up to 3. Is the eigenvalue. This means, with minus, of course, this means it's quite fast. I think the time in order to see the dynamics should be in the order than 10 of minus 3, more or less. This means I would like here to write 10 up to minus 3. Let me see if I'm able. Probably so is too much. How I think 10 times too small. Let me see if now we can see something. Because of course I need 7 times, 10 times the rising time. And the rising time can be seen a little bit related to the one divided real part of the lambda. Do you remember I told you that the dominant time constant, we have just one, is the minimum, excuse me, the maximum tau. Tau is the maximum between one divided real part of lambda. We have just one real part because we have two complex imaginary solutions. This means the dominant is 10 minus 3. I look correctly. And you have to put, you remember, 5 times, 7 times. I put here 10 times is okay too. We can see optically that even though I have an error everywhere, 10%, but try to do at home. If you put also 50%, of course, in this case, we can see that the transit will change. The transit will change. If you want, I can do that. The transit will change. But we will nevertheless achieve the goal without bias. This is a big advantage. Let me put without sharing the error, I don't know, 50% everywhere. In L, in C, in R, in the parameter. To remember, last time I told you that the parameter I put 50%. Yeah, we can see that we have an error, the transit change. We have practically also oscillations we can see here because the design now is considered ideal lambda 1, lambda 2, which reflects the two eigenvalue of the system. We can see the oscillation, but the transit ended somewhere, and mathematically we converge to the goal. Okay, with this example, we concluded the first part of the course, which is dedicated to selected topic in robotics and automation. And then we will start with a new chapter dedicated to sliding mode control, which is extremely important because it's, before closing, I forgot. You remember I told you that everything works, in particular this track without bias, if R is constant. If R is the goal, if R is not constant, the sinus, we will have a bias. Now, of course, it could be that the bias is very small, and this independently, let me say, on the knowledge of let me simulate a little bit longer, on the parameter not. I don't know. Let me simulate also longer. We will reduce if I simulate longer, but will never be exactly 0. Even though it seems. But we can see. We can demonstrate, nevertheless. Let me show you another thing. And then we take a rest, and then we will start with another. 1 second, I come back to you. I put it now. I don't know if it's visible. No error in the parameter. We can see nevertheless that even though small, we have an bias. Because what I told you about this robustness or in general steady state error zero, the basic knowledge or the basic idea, the basic assumption to demonstrate this was that R of t was constant. If R of t was constant, if the system is asymptotically stable, we have a U2 constant, I1 constant, and then Xi constant. The derivative of Xi means zero. But if R is constant, and known in this sense, our goal, U2 is constant, is equal R, because the derivative of Xi is equal R minus U2 in our case. The same consideration can be done if the output is I1. Question and homework. Try to control, instead of U2, I1 is trivial, but also easy if I ask you, try to control UL. Because as I told you, once you describe the system, you can control everything. If you describe the system in state, excuse me, I forgot, but it's clear. No, what I give you an idea. UL is L multiply the derivative of IL divided T. Think about it. Then you have to combine the information of the I1 is through inductance, to the inductor, to be precise, but the inductor is characterized by the inductance. This means we can change the wording. We have a current I1. Through the inductor, we have a current I1. This means we have an expression of derivative I1. No? Think about how we can control this. Think, and then we can do the exercise next time. Let me take a rest. In the meantime, I found the material for the next topic, which is sliding mode control, also related to this example here. If the signal is not constant to be tracked, we cannot apply, we can apply, but we have to be aware that we have a bias. But we can consider another method based on a controller which is non-linear. And then we can consider also to track a non-constant signal. Okay, let me take more or less 20 minutes as before. As we have seen, independently of the knowledge of parameters in this example, but we can generalize. If you think how I demonstrated everything which I told you is independently of the parameters, because in the context of the derivative of xi, this augmented state or pseudo state or the state of the controller, the derivative of xi with respect to the time equals R of t minus u2 in our case, or the I1, or it doesn't matter what. We can see that this equation does not depend. This is the key point, that not depends on the parameter. But in this case, is the idea why we have the steady state robustness, but R of t must be constant. Otherwise, well, we have seen that this method does not work. Can be used, of course, can be used because very often we are considering constant value to be controlled. A robot should be positioned in a constant, should remain in a constant position. Do you remember yesterday I told you if somebody of you attended the class of robots, the Segway that should be controlled in the arm and this more or less in this position. This means uh, the value is almost constant. The idea of almost constant could work. I mean, if the dynamics of R of t is relatively slow with respect to the dynamic of the system, in this case, of course, we can nevertheless apply, even though mathematically we have a bias. I mean, let me come back on this. Could be nice, this example. Now here we have a relative fast dynamics. No? Do you remember? We also have seen that the time constant is around 10 of minus 3. Yeah, but if I slow down the velocity of the reference signal, RT was this sinus, no? Look, if I slow down again, of course, this bias we will reduce. But if I increase, this bias we will increase. Why we have slow down, we will reduce? The reason is that the system sees the reference more constant, let me say, even though more constant doesn't make more sense, sees the system a little bit less variable. This makes sense. Let me show you if I'm able to show you. And then we will start, nevertheless, with this slide mode control. In case we need to achieve more precision, of course, we have to use different approach or approaches. 1 second, I am a little bit ill, but not much. Let me show you. Just to understand what is the meaning of constant with the slow dynamics. Slow dynamics cannot be say slow input signal. This means I reduce the frequency, 0,1. Excuse me. The bias should be reduced. Of course, we have seen that we have a relatively small bias, but let me see. Should be nevertheless visible that I will reduce also, the bias will be reduced. I don't know if it's really visible. Let me see. It's difficult to judge. Should be nice if I put a metric. Huh? Let me show you what I intend with the metric. This could be also useful in our contest in the project. Let me this could be nice. This I would like to do. It's more important now today. Speak about shortly about this instead of. But in any case, I will start with the sliding. Huh? We will see. Let me see how much time I need to clarify this concept. If I consider the difference between what is, I share, let me see. I am considering now the difference. Where is the difference between was is uh, and what should be? Then I will consider a square. And then I do the integral of the arrow square, which is the possible metric. Not the unique one, but it's the possible metric. Let me show. I go under math operations, and there is the possibility I didn't share here uh, to do the product. We have many way to realize the product. This is one of them, probably not the best. I multiply, and then let me integrate. That this means is again the energy of error, no? And then I will put here. If you go under sinks, you can find display. This is the integral of the arrow square. Let me run. Very small. uh, I don't know if we can trust this small value. Let me simulate a little bit longer. So I don't know really small. 1 second. Let me simulate 100. So we have something more. Oh, this is really strange, this. I don't understand exactly why this value. Let me see how it looks like. It's really strange. Probably we cannot trust because this value which I have here is positive because it's Santi square. Hmm? The integral of Santi square is positive. If you have a negative, I think that we are close to zero. Let me consider probably another function because it's numerical error, which realize the product. Let me see. Could be that the problem is this. Let me see. Under math operations, let me see. Let me consider this. The absolute value. You can find this under the under you can see here under the library browser using the library or under the library the name is the math operations. Let me see what happens now. Okay, now it's better. It could be that this product makes some numerical errors. No, don't forget when we are working with a computer that is machine. Okay, we have here uh, 7 up to minus 3, right? Now, let me uh, come back here on the system, on the signal, and let me put instead of 0, 1, I will like to show you, then this means the signal is more variable. Huh? Let me see if we obtain a larger steady state. Even though, again, here I measure everything. This means how possible to say is not exactly correct, but should be visible, nevertheless, a larger error. Let me run with the same time, of course. And let me share now. I am running. Let me share the picture, the scheme, excuse me. Let me share the scheme again. I already ran. We can see that the error is much larger. Huh? It's confirmed exactly what I told you. Very often, even though we have a variable signals, we can see it's much larger. But if the variability of the signal is much less with respect to the dynamic of the system, much less, of course, it's not a scientific concept, but anyway, we can build some criteria in order to estimate, also heuristically at the end, how is the error. Huh? But in general, if we want to have a bias exactly 0, we cannot use this method if r of t is not constant. Now, let me introduce in these few minutes what I will start next week. The method which is very often used in robotics and automation, really in the application, is one of the most used. We will see, I will reconsider also the example of yesterday in the next lectures, because came from the lab of robotics. I considered basically in the system to understand the methods, and then I flesh out an interesting example. But of course, this example is an example for a master thesis, for a thesis in general, also bachelor thesis with different focus, because it's extremely complex to explain in a lecture. But in any case, it's understandable. I hope if you, yesterday, you attended the classes, it's understandable after this first example we didactically introduce uh, the application in robotics of this sliding mode control, even though yesterday I didn't formalize it in the context of sliding. 1 second, I open now the lecture last week, the next week. Mm, easier. Okay. Look how it looks like the lecture of next week. It is a good idea to introduce just the topic. And second, I found now, I put it in a folder which is not exactly this. Ah! Okay, okay, I think it's this. No, I am stupid. I saved before during the when we stop the lecture. No, we take a rest. I use this time also to. The problem is I have so many material. Now I forgot where I put it. Okay, 9 seconds. I forgot where I put it, but I found them. I think it's here inside. Okay, let me share, and then next week we will start officially considering this slide here, elements of applied slide remote control, in which we will see together the fundamental elements of this method, of this technique, I would like to say. The slide remote control is robust. About robust, this word we used also today. In some books, some author, they say is unsensible with respect to uncertainties and disturbances. Anyway, I don't want to specify these differences. Sometimes it's basically the same. Unsensible means more than robust. Basically, what we have that even though I don't know parameters, even though some assumptions are not guaranteed, which one? R of t constant is an assumption or conditions. This method allows nevertheless to achieve results. Results, what is the meaning? To obtain the goals independently of this condition, knowledge on the system and condition of signals. I will tell you starting with the easiest system which I have. The system here basically cannot be applied. I mean, it can be applied, but does not represent any robots, any automation system, but allows to introduce this complex, relatively complex method, which really is so strong that we will see in your career, if you go ahead with control, with robotics, that is really, really effective. We have a state, we have an input. We don't have easiest system in the sense of control. You and input must be considered. We will see that the idea is if I have an initial state, an initial condition, by initial condition, I told you many times. The idea is I will show you using this goal, steer the state to zero, how we can steer the state to zero considering a linear approach, something like today, state space controller. And then we will see what happens if I consider more complex, if you want, control system, a non-linear control system, which can be applied also in linear case. This is in a linear case. No? But of course, we will see advantages and drawbacks. But we will see that if the system is complex, if the system does not accept in its control strategy compromise between conditions on signals, if the system does not accept to be approximating in the goal, if the system to be controlled is not known in terms of parameters or in terms also dynamics, it worthwhile to pay this price to apply this complex controller in order to obtain results. Okay, I think instead of now starting with this lecture, but now in any case, I told you what I intended to start to do next week. Also, we will conclude. I don't know if I may be able to conclude the slide in next week, but in any case, I will do examples, starting from easy examples, and then the idea, the first example. Also, I can tell you also there's a second example of the lecture of yesterday. Could be nice to do that, if not next week, after next week, and then to conclude a little bit with this sliding. I would like to conclude here today what we have. We have concluded with this classical approaches which can be applied in any kind of system, also in robotics and automation. I will upload in our electronic platform. I think I don't know how we'll organize. It could be that I will build a folder in which I will include, I will write all material until today is 28, which I will, if you go inside, we will look at the classical. I don't know, but in any case, I will be, I hope clear what is there. And I would like to send you today, tomorrow, when I have a little bit time, per email too, parallelly. I will organize in our electronic campus, let me say, uh, per email also all material till now. So it's clear, no? With email, we have all material till now. And I don't know how we'll organize in the best way in the electronic campus. But in any case, the material is there somehow. No? I will upload there also. Also. Thank you for your attention. I am here now for questions. If you don't have questions, of course, we will see next week, more or less at the same time. Let me close the lecture now here. Thank you for your attention.